What is the Lorentz force in electric and magnetic fields? Imagine a tiny charged particle floating in space, feeling invisible pushes and pulls from electric and magnetic forces. These forces shape how particles move in the world of electrical engineering and electromagnetism. The Lorentz force is the name of the total force acting on that charged particle when it is in both electric and magnetic fields. It combines the effects of electric forces, which push or pull charges directly, and magnetic forces, which influence moving charges in a different way. If a particle has a charge, which is a measure of how much it can be pushed or pulled, and it moves with a certain velocity, the total force on it depends on both the electric and magnetic fields around it. The electric field is like an invisible force field that pushes charges along straight lines. The magnetic field, on the other hand, affects moving charges by pushing them in a direction perpendicular to their motion. The mathematical way to describe this force is through a simple but powerful equation. The force equals the charge times the sum of the electric field and the cross product of the particle's velocity with the magnetic field. This means the force from the electric field points in the same direction as the electric field itself. The magnetic part depends on the particle's velocity and the magnetic field, and it acts at right angles to both. To visualize the magnetic force, you can use the right-hand rule. Point your fingers in the direction of the particle's velocity. Curl them toward the magnetic field. Your thumb then points in the direction of the magnetic force for a positive charge. If the charge is negative, the force points in the opposite direction. This force law is fundamental because it explains how charged particles behave in different environments. It is behind how electric motors turn, how generators produce electricity, and how particles move in devices like cathode ray tubes or plasma chambers. It also helps us understand how electromagnetic waves travel and how signals are transmitted through antennas and transmission lines. In practical electrical engineering, the Lorentz force helps us design motors that convert electrical energy into mechanical motion. It guides the creation of sensors like Hall effect sensors, which detect magnetic fields by measuring the force on charges. It also explains the behavior of particles in vacuum tubes and plasma devices, which are used in various high-tech applications. In essence, the Lorentz force is a key concept that ties together electric and magnetic fields. It shows us how forces act on charges and how those forces are responsible for many devices and systems we rely on every day. Understanding this force helps engineers design better motors, sensors, and communication systems, making it a cornerstone of electrical engineering and electromagnetism.